This is section 2.7, part A. We're simplifying radical expressions and imaginary numbers, specifically in part A, square roots of positive numbers. So the first little note here is that we know some numbers can look different but have the same value, such as 1.5 can be written as the fraction 3/2. 4/6 can be reduced and written as the fraction 2/3. -10 divided by 2 can be simplified to be -5. And 35% can be simplified to 0.35. What we're going to be doing in this section is simplifying radical expressions so that I have a radical equal to a simpler radical rather than a fraction equal to a simpler fraction. Okay, similar idea. So first of all, for these two radicals here, the square root of 45, the simpler version is 3 times the square root of 5. And we're going to use a calculator real quick to show that I get the same decimal value for each, showing that they are really the same number. Okay, so in my calculator, the first value, square root of 45, is and truly equal to 3 times the square root of 5. So I get approximately 6.708 for both of them. That shows that they are the same value. The next one, the square root of 3/8 can be simplified and written as the square root of 6/4. So let's just check that they have the same value. The square root of 3/8 simplifies to, let's see, it was the square root, oops, wrong button there, the square root of 6/4, same decimal value, approximately 0.612. Okay. Now, going to look at a few definitions here for what it would take to get a square root in the simplest form. The first is that there need to be no perfect square factors inside the square root. So no perfect square factors. The second is no fractions inside the square root. And the last one is no square roots in the denominator. So I want to make sure that each of these three things happens in order for my radical to be reduced. That's why this one was reduced, because the perfect square 9 went into 45. I had to pull that out, square root of 9 being 3 is the coefficient. Those are not a fraction, so that was not simplified. The end result is simplified. Before we can really begin, we want to make a list of perfect squares so I know what numbers I'm going to be able to divide out. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, and 15 squared is 225. Okay, just want to have this list of perfect squares handy, because anytime I go to simplify an expression, I want to be able to divide out a perfect square. No perfect square factors means that none of these numbers that we've written down can divide a simplified radical. To simplify, we're going to use the product property, which says that the square root of AB can be separated into the square root of A times the square root of B. Okay, so again, using this first property first, I'm simplifying. The square root of 28 is not considered to be simplified because a perfect square, 4, divides into it. So I could write this as the square root of 4 times the square root of 7, since 4 times 7 is 28. I can do the square root of 4. The square root of 4 is 2. So this simplifies as 2 times the square root of 7. That would be the simplified answer. Okay. In the next one, 80, I need to find the largest perfect square that divides evenly into 80. So I know that 16 goes into 80. So I'm going to separate this one into the square root of 16 times the square root of 5. The square root of 16 is 4, so this will simplify as 4 times the square root of 5. I just want to make a note about 80, because perhaps you hadn't thought of 16 first, but had thought of 4, since 4 also goes into 80. If you had instead broken 80 into square root of 4 times square root of 20, that would have given you 2 times the square root of 20, but that wouldn't have been finished because 20 can be broken down. That would have given you 2 times 20 is the square root of 4 times the square root of 5. So you would have had 2 times 2 square root of 5, and you would get as your final answer, again, 4 square root of 5. So it's to your benefit to choose the largest perfect square that divides evenly into a number so you can do it in fewer steps. Moving on to the next one. The next one is the square root of 75. If I'm looking through my list of perfect squares, 25 goes into 75. So I'm going to separate this into square root of 25 times the square root of 3, since 25 times 3 is 75. 25 is a perfect square, so the square root of 25 is 5. I can't do the square root of 3, so I leave it in the radical. Radical is another word for a square root, by the way. In the last one here, 600, you can divide by 100. So I'm going to write this as the square root of 100 times the square root of 6. I can do the square root of 100. That gives me 10. I can't do the square root of 6. So that leaves me with 10 square root of 6 for the simplified version. Okay. We're going to work on the next two pieces of getting my radical simplified on the next page. So the next piece says that I can't have a fraction inside of a square root. So to separate these, I'm going to use the quotient property, which says that if I have the square root of a over b, I can write this as the square root of a over the square root of b. That's going to break my fraction down so that I have separate square roots, no one fraction inside of the square root. So for this first one, the square root of 5 over the square root of 36 would be my first step. Square root of 5, 36 can be broken down into the square root of 5 over the square root of 36. I can't do the square root of 5, but I can do the square root of 36, which is 6. So this simplifies to square root of 5 over 6. Next, I can write this as the square root of 10 over the square root of 64. I can do the square root of 64, and so I'm left with square root of 10 over 8. Now, in the next one, notice that I can't do the square root of the denominator, 27. Here, notice that I could have reduced, but I did not reduce 10 and 64 because the bottom was already a perfect square. The bottom was already a perfect square, so I wanted to leave it as 64. Oops, perfect square. However, here, the 27 is not a perfect square, so I'm going to want to reduce first. Reducing is one of my techniques for rewriting. So if I reduce this, 15 and 27 can both be divided by 3. If I divide them by 3, it's going to give me 5/9. And now I can separate it into square root of 5 over square root of 9. 9 is a perfect square now, so now this is going to simplify to square root of 5 over 3. Okay. So I have to choose my techniques. Sometimes I would like to reduce before I break it up, and sometimes I wouldn't, depending on if the value in the denominator is or is not a perfect square. Okay. Last, sometimes the denominator just isn't a perfect square and reducing isn't going to help, in which case I'm going to need to rationalize the denominator. Rationalizing the denominator is the other way to get rid of a square root in the denominator, and it's going to be accomplished by multiplying by the smallest factor that will create a perfect square in the denominator. So in this first one, the smallest perfect square that 7 goes into is 49. So I'm going to multiply top and bottom by the square root of 7 to try to create a square root of 49 in the denominator. It's like getting a common denominator. It's like what I would do with any fraction that I wanted to change the denominator of and multiply top and bottom by the same thing. The top becomes 4 times the square root of 7. The bottom becomes square root of 49. Numbers that are outside of a square root stay outside of a square root when you multiply them together. Numbers that are inside of a square root can multiply together inside the square root. So this is going to be 4 square root of 7 over. I can do the square root of 49 and I get 7. As you probably noticed, you can't reduce a number that is out of a square root with a number that is in a square root. So there's no way I could reduce these 7s because the bottom is out of the square root and the numerator is in the square root. Okay. So same thing in part B. If I separate this, it's not going to do me any good to write square root of 2 over square root of 5. So I need to rationalize by multiplying by the smallest perfect square that's going to make this 5 a 25 in this case, because 25 is the smallest perfect square that 5 goes into. So multiplying by square root of 5. My numerator is going to be square root of 10, square root of 2 times square root of 5, square root of 10. My denominator would be square root of 25, 5 times 5. I can do the square root in the denominator. The square root of 25 is 5. So my final answer here is square root of 10 over 5. It's considered simplified because there's not a fraction inside the radical, and there's not a radical in the denominator, and no perfect square like 4 or 9 would divide into 10. Okay, 2 more here at the bottom. Okay, 12. 12 goes into 144, but that's not the smallest perfect square that 12 goes into, because 12 also goes into 36. So since 12 goes into 36, I just need to multiply by the square root of 3 to create a perfect square in the denominator. That's going to make this negative square root of 21 over square root of 36. And that's going to be negative square root of 21 over, I know the square root of 36 is 6. Always look for the smallest perfect square that you can create in your denominator. Had I multiplied by square root of 12, I would have gotten the same thing, but I would have had many more steps as I would have had to reduce my radical. Okay, 32, the smallest perfect square that 32 goes into is going to be 64. Since 32 goes into 64 twice, I can multiply by square root of 2 on top and bottom. That's going to create a square root of 18 in the numerator and a square root of 64 in the denominator. The square root of 18 can be simplified. I can write that as square root of 9 times square root of 2 because I can do the square root of 9. 64, the square root of 64 is 8. So the final answer is going to be the square root of 9 is 3 times the square root of 2 over 8. So I had to rationalize this one, get the denominator out of the square, and simplify the numerator since the numerator happened to have already been a perfect square in the 9. Okay, so I had to bring out the 9 in the square root of 2. Okay. Flip our page. All right, so at the top of this next page, we have a statement that says, recall that we can simplify a quotient containing a binomial and a monomial by distributing the division. So I can distribute the divide by 3 to both parts in the numerator. So this gives me 15 divided by 3, or 15x divided by 3, plus 12 divided by 3 simplifies to 5x plus 4. 15 divided by 3 is 5. 12 divided by 3 is 4. Another approach to simplifying this division would be to factor the numerator. You could factor a 3 out of the numerator. That would leave you with 5x plus 4 and over 3. And then if you have a factor of 3 in the numerator and in the denominator, those can reduce. So either way, we're going to get 5x plus 4. It doesn't matter which method you use, whether you're distributing your monomial division or if you are factoring. I want to be able to get this reduced to the 5x plus 4 in either case. Okay. Now, each of these fractions down in example 4 is going to be able to be reduced by the same principle, either dividing them by a common factor or factoring and then reducing. Personally, I prefer to use the top method, but if it is makes more sense for you to use factoring, by all means, go ahead and use factoring. Okay. So what I see here is that I can reduce the coefficients. So coefficients only, not the value inside of the radical. But if I can reduce all 3 coefficients, in this case, the square root of 7 is taking the place of the x right here. I had to be able to reduce all 3 coefficients, the 15, the 12, and the 3. It didn't involve the product of x. But all 3 of my coefficients by the same number, in this case 2, divide them all by 2, I can reduce this fraction. So if I divide by 2, that's going to be 4 plus 6 divided by 2 is 3, square root of 7 over 5. Okay. That is the radical quotient simplified. Now, of course, you could write this separately as 4/5 plus 3 square root of 7 over 5. That would be the same thing. It would just be written as 2 fractions instead of 1 fraction. Okay. In part B, looking at my 3 coefficients, the 35, the 15, and the 45, they can all be divided by 5. So let's do that. We're going to get 35 divided by 5 is 7. 15 divided by 5 is 3. So 3 square root of 3. And 45 divided by 5 is 9. Okay. As a single fraction, that's as reduced as this gets. But if I separate this one into 2 fractions, it would be 7/9 plus 3 square root of 3 over 9. Written as 2 fractions, you can now reduce the second fraction further. So if I wrote this one as 2 fractions, it would be 7/9 plus the square root of 3 over 3, dividing 3 and 9 both by 3. Okay, now these are both equally simplified, and it's going to be a matter of personal preference which one you choose. In some contexts, you'll want to separate them, especially if your number is complex, but in the most cases, you're able to leave them either form. What I want to make sure I don't do is reduce the 3 and the 9 in the one big fraction, because this 9 does not also reduce the 7. 9 needs to stay in the 7's denominator. 2 more on this page. In the next one, there is no coefficient in front of the radical to reduce, so I could not reduce my entire fraction. However, that radical 12 is not simplified, so we're going to start there. We've got 14 minus radical 12. You can break down into square root of 4 and square root of 3, all over 8. Then you've got your 14. The square root of 4 is 2, so minus 2 square root of 3 over 8. Then you're ready to simplify, because you can simplify the 14, the 2, and the 8 all by 2. So then you're going to get your 7 minus the square root of 3 over 4. 14 divided by 2 is 7. 2 divided by 2 is 1, so I've got 1 radical 3 over 8 divided by 2 is 4. Okay. In the next one, same case, I don't have a number, a coefficient that I can reduce, but I can break down the square root of 18. So if that's 6 minus the square root of 18 can be broken into square root of 9 times square root of 2. 18 is 9 times 2. And then you can break down the square root of 9. So that's 6 minus 3 times the square root of 2 over 12. Now all 3 of my coefficients can be divided by 3, so that gives me 2 minus the square root of 2 over 6. When there's no reducing I can do, it's nice just to leave it as a single fraction. Sometimes, if you can reduce one of the pieces, you like to break it into 2 fractions. So this one would be considered 2 sixths minus square root of 2 over 6. The 2 sixths reduces to 1/3 minus the square root of 2 over 6. And again, these are equally correct. Both of them are simplified versions. They're just different versions. One is the single fraction version, and one is the 2 fraction version. Before I go any further, I just realized I made a mistake right here. I was supposed to be dividing these all by 3, and it just came to me that this should be a 4, right? 12 divided by 3 is 4. So this is also a 4. And that actually makes this last piece a half right here. Okay, I got all the numerator part's right. I'm sorry about that. I was supposed to be dividing by 3, and at some point when I saw the 2's in the numerator, I think I accidentally divided by 2 in my head. So hopefully we can make that fixed real quick right there. Okay, 3 in common, divide them all by 3. 6 divided by 3 is 2. 3 divided by 3 is 1. 12 divided by 3 is 4. And from there, I think that we are now correct. So luckily I caught that, but sorry if that caused you any confusion. All right, that is the end of part A.